actually in the soil mechanics to determine the shear strength of the soil. So we found out that from 1 coulomb failure envelope, there's 2 stress parameters: collision intercept and the friction angle, right? And to get the C and the P, we can perform the laboratory test or field test. And in the laboratory test, the most common laboratory tests are the Triaxial test and Triaxial test. Triaxial test has to be done it, and Triaxial test, we're gonna get a hint from this class, and you take the sort of things too, and you get more idea about that. In the field test, instead of taking the sample from the field and trim it and place it on the Triaxial test machine or the Triaxial shear strength machine, you can just push some instrument to the ground and just measure the shear strength directly. That's called the field test method. There are several field test methods like base shear, pole base, pole count, but we don't cover these methods in this class. When we look at the field condition, this is the initial condition before construction, and there will be a vertical loading, vertical stress by this overload stress and the horizontal stress from the K naught W. And when you construct a structure, you will increase the delta sigma, right? You may increase the delta sigma at the horizontal and the vertical too, but the magnitude of the increase or stress increment will be different, the horizontal and the vertical. And if we idealize the vertical stress only, then we can assume that the vertical stress becomes constant, and while the vertical stress increases at some point, and also will get bigger, and it's going to touch the failure envelope, and then it becomes failure. So when we perform the laboratory Triaxial test from the field, imagine that you have a sample from the field. Then once you get the sample from the field, all the stress will be released. So the stress condition is 0 right after you take it. Then you place it on the Triaxial test machine, and then you bring up the stress condition to the field condition to emulate the field condition. So the sigma B and the sigma H will be re-simulated by increasing the confining pressure, and then you apply some other extra deviatory stress or the vertical stress to see how much the soil can sustain more stress until it fails. And when you perform the Triaxial test, you're going to increase this vertical stress delta sigma. When you perform the Triaxial test, you're going to increase this tau, the horizontal stress. Triaxial test looks like this. We're going to show you the machine there. You have a cylindrical sample that stands alone by itself, and there's a porous stone at the top and bottom that allow the water drainage going in and out. And you have a rubber membrane that separates the soil and soil pore fluid from the outside confining pressure, confining fluid. So there's a cell pressure line that maybe use the gas pressure or the water pressure to confine the soil around the soil metric. Vertical stress and the horizontal stress will be given by this cell pressure. And then there's a deviatory stress that increases the sigma 1. Sigma 3 will be fixed during this stress increase, but the sigma 1 will increase because you're applying the more vertical. And there are two drainage lines. There's a bottom fluid port and the upper fluid port that can close the valve or open the valve to control the drainage. So if you close the valve at the pore pressure line and the back pressure line, you don't allow any water escape or water going in. or inflow or outflow is all closed. If you open the valve, and while you open the valve, you can touch the sample, right? Then you are allowing the water to escape. So that's the difference for the drain condition. We're going to see how that's important in this prediction. So when you apply the stress, as you increase the vertical load, it's going to compress, and when the soil cannot take any more, then it fails. It slides down. What's the angle of this failure plane? Do you remember? How is this failure plane angle is determined? 45. It's not just 45. 45 plus P over 2, the friction angle. So depending on the friction angle, the angle of the failure plane will be determined, ideally. But it's not always the same. But in general, it shows the failure plane proportional to the friction angle. So it has this kind of a peripheral surrounding the equipment together. Maybe this one measures the pressure, this one measures the flow pressure, this one measures the volume, and there's a loading force measurement cell, and there's a displacement sensor, and there are several valves and fluid lines. Okay, so before we, Shelby tube. I've shown you before the Shelby tube, or the thin wall tube. We can use the thin wall tube to take the sample from the field of interest, and you're going to extrude the sample using the extruder. When you take the sample out, you place it in the sample holder and trim it carefully, not to disturb and not to change the facing of the soil. And setting out the sample with the triaxial cell and put the membrane on it. So this is the white jacket is the rubber membrane. So that the outside fluid cannot go in and the inside water or the gas cannot go outside. There you can see there's a 3-port. One is for the cell pressure line, and the other 2 is for the flow pressure. Then when you assemble all of that, you can close the top cell and give the water to make it full of the water inside, and as you apply the water pressure, you can confine the soil and make it compressed to incorporate stage. Sample preparation. Then you after you've done this one, you will place the whole triaxial cell on the loading plane, and this loading plane will increase the load at a certain constant rate. Here, what you measure is the vertical force and vertical displacement, how fast it settles. Excess flow pressure will be dissipated right away, immediately. Right? So that's why we perform the drain looking test in the case. When you have a clay and the loading is very slow in this case. So first step loading is test and you wait about one hour, 1 year, and then another loading comes here and wait another 1 year. Then the loading rate is very slow, so that the excess flow pressure has enough time to escape, to be dissipated. So then it's the same in the drain loading condition. So that's why we allow the drainage during the CD test, and we're going to use that C and P step parameter for this kind of analysis. So if we construct really fast, then it doesn't allow any time for water to escape. So it's going to increase the excess flow pressure. So then you have to close the valve, and we're going to get the other step parameter using the other drain loading test. So it's depending on how permeable soil is and how fast your loading is. Velocity is So when embankment is constructed very slowly in layers over a soft plate project, then range shear strength will be used to analyze the safety. Or same with the steady state CPG. So in this case, steady state CPG will be here is the upper upstream, this is downstream. So from the higher total head to the lower total head, water will flow. So water will flow like this, and because of the CPG force, the soil can slide down like this. Right? So, and this red arrow is resisting force against the slide. So in this case, because the CPG is already happening, so the water is escaping and the flowing freely, so we do use the drain resistance. The excavation of a natural sloping clay also will be the case for the drain drawing. So CD, the consolidated drain test, simulates the local condition in the field. C sub D and P sub D should be used to evaluate the long-term behavior of the soil. While for the long-term, the loading condition is very slow, so it is relatively low. Next is the consolidated drain test.